Good afternoon, everyone, and welcome to this afternoon's webinar. I know we've still got people connecting, but we'll go ahead and get started as it's 1 o'clock. Our presenter today is Bart Morris. Bart is an applications engineer at HBM with 27 years of experience in a variety of areas within the company, including manufacturing, service, technical support, international support, sales and application support of all of the high-speed data acquisitions and sensors, and recently has moved his focus even more over to strain gauges. Bart, it's all yours.
All right, thank you. So today's seminar is on the introduction to strain gauges. Now, strain gauge measurement techniques touch on two specialist areas. They deal with mechanical engineering and electrical engineering. And what today's seminar will do will touch on the science behind the strain gauge. We're going to do a history of the strain gauge and where it came from, discuss the theory on how they work. We're going to discuss the process for preparing the work area for the installation of the strain gauge, and discuss some of the techniques required to attach strain gauge to the material under test. Now, mechanical engineering and the laws of mechanical stability required that we needed some way to test structural part assessment. So basically, this is the strength of material calculations of machines, buildings, vehicles, aircraft, etc. This method is satisfactory if we can know component loads, both qualitatively and quantitatively. But there are problems arise if the loads are unknown or if loads can only be approximated. Previous workarounds in the past provided excessive safety margins. So if you were to think of medieval churches with the walls 8 feet thick, and other expensive workarounds such as overdimensioning. However, modern design strategies need to incorporate the savings in the material costs, take into effect safety concerns. We needed savings in weight for aeronautics, automotive, etc., and then to provide a long service life to our components. In order to satisfy these requirements, material stresses must be known, and measurements under operational conditions must be made. Now, with material stresses, it's virtually impossible to determine under operational conditions. X-rays would be suitable, but it's not very practical if the device or the item under test is large. In 1678, Robert Hooke found a relationship between material stress and deformation or strain. So this deformation also occurs on the surface of the object and therefore can be measured. The solution to this problem is the strain gauge. It's a very small device, it's accurate, and it's inexpensive. From the time of Robert Hooke, mechanical devices were used. The initial tools to develop and measure strain were a lever device with a ratio of 1,000 to 1. So this diagram on the right shows an early tensometer with a double lever mechanism. The body of the device had a fixed knife edge that was put into the material, and then we had a lever with a movable knife edge. It provided a coupling bar and then an indicator and a scale. This had several drawbacks, including that only static processes could be observed. Strong clamping of the tensometer to the item under test was required. The test sample had to be fixed. The size of the device limits its use, and it only gives correct results for uniform conditions. Local conditions such as the weather may be unobtainable for the observer, and there was no way to automatically record any of the measurements made. So an electrical measurement technique would provide the solution. In 1843, Sir Charles Wheatstone described a bridge circuit for measuring electrical resistances. Unknown resistances are compared with well-defined resistances. He developed calculations of resistance changes using Ohm's law, and it was found that this was well suited for measuring small changes in resistance. The two diagrams below show you the Wheatstone Bridge in its current form. The one on the left is the design that Charles Wheatstone drew up, and electrically the one on the right is exactly the same, but most people are used to the one on the left. In the 1930s, two engineers working independently invented the strain gauge. Edward Simmons of California wanted to measure force impulses exerted on a specimen from a pendulum ram, and he ended up using silk thread and some thin resistance wire. Arthur Claude Ruge from Massachusetts wanted to measure stress from simulated earthquake vibrations, and he ended up trying various methods. What he ended up doing was taking a very small, thin resistance wire and made it meander shape and glued it to a bending beam. He then developed a production method, and because of all of this, should be considered the father of the strain gauge. Ruge's production strain gauge was first too cumbersome. World War II was just about to start, and manufacturers of aircraft and tanks and other military vehicles required mass production. So he came up with a simplified support structure, and this allowed the strain gauge to become easier to produce and smaller in size. Since the 1950s, the method of using the printed circuit makes the quality of the strain gauge consistent, and this method is used today. So if you look at the image on the upper right-hand corner, that's the original strain gauge, and it had to be secured to the test article. The image on the lower left-hand corner is Ruge's wire wound method, and you can see that it's very close to the printed circuit or foil strain gauge that we use today. All right, so the theory behind the strain gauge. The principle is mechanical or thermal. A change in the length of an object due to a mechanical strain of that object results in a change of resistance of the strain gauge attached to it. Also, a change in the temperature of an object also changes the length of that object, also causing a change in the resistance of the strain gauge attached to it. And so we have mechanical forces or thermal forces on our original object, and our strain can be defined as a change in length over the length of the original object. Now, this change in resistance can then be converted into a unit of measure. The change ends up being very, very small, micrometers of change per meter of overall length. Now, this change in length can be either positive or negative. Strain is positive if the change in length is positive, so that's a tensile stress. Strain is negative if the change in length is negative, compressive stress. So microstrain is used as the units of stress in the United States. And you can see that stress is a proportional value. And as the change in length is very small, we use the term micrometers. So elsewhere in the world, you'll see the term micrometers per meter as opposed to microstrain. Now, Hooke's law states that an object that quickly regains their original shape after being deformed by a force. With uniaxial stress, we have our material stress is equal to the modulus of elasticity times the strain. So again, tensile stress is positive, compressive stress is negative. So this is a very simple equation, but again, this is uniaxial stress. If we have biaxial and multiaxial stress, the equations are much more complicated. This is a diagram of a stress-strain curve. So on the y-axis, we see our stress, on the strain on the x-axis, and it's seen that at a certain point, an object will reach its limit of elasticity where the item will not bounce back to its original shape, and at that point, the object becomes deformed. So going back to the strain gauge, let's imagine that as a piece of wire. So the top diagram shows our piece of wire without any kind of strain. With a positive strain, we stretch the wire and it becomes thinner and longer. With compressive strain, the object becomes shorter and fatter. And so the change of resistance can be considered by the equation below. So a change in resistance because the wire is changing its physical geometry. What a strain gauge does is transform the strain applied into proportional change of resistance. The relationship between applied strain is the change of length over the length of the object, and the relative change of the resistance of the strain gauge is described by the equation. Change in the resistance over the original resistance equals K times the strain. The factor K is known as the gauge factor, and it's a characteristic of the strain gauge. This gauge factor is measured by the manufacturer and then documented and is placed on the strain gauge package. Typically, you'll see a value of around 2 or 2.02. Every package that you get from HBM or other manufacturers will have a gauge factor included on the sensor. The construction of the strain gauge, you have a carrier material, and inside it is that meandering measuring grid that's embedded within that material. Long measuring grids are suited for inhomogeneous materials such as concrete or wood, and short measuring grids are suited for measuring local strain. Now, the strain gauge inside the Wheatstone Bridge. There is a relationship between the applied strain and the relative change of the resistance of the strain gauge. The strain gauge converts mechanical strain into a change of electrical resistance. The gauge factor is a characteristic of the strain gauge and is found experimentally. Because these changes in resistance are very small, measurements with an ohmmeter are impossible. Oftentimes, the change in resistance is about 0.1%. So if we were to take a typical strain of 1,000 microstrain for 120 ohm strain gauge and perform the math, the change in the resistance over the original resistance times the K factor, or equals the K factor times the strain. And solve for the change in resistance, we end up finding that 1,000 microstrain deflection ends up being a change in resistance of 0.24 ohms. In order to make this measurement, we need to use an amplifier. Now, these amplifiers must be high-gain amplifiers and have low noise, or else they will interfere with the signal quality. Alright, so this is our Wheatstone Bridge circuit laid on its side. And in this case, we have a potential divider. We have 4 known resistances set up in a Wheatstone Bridge configuration with an excitation voltage of 10 volts. All of the resistances are in equal value. And if we want to find the voltage at point UA, because of the equal resistances, Ohm's law states that the voltage should be 0 volts. Now if we consider one of the resistors changes, R1 in this case, changes to 6 ohms. All the other resistors maintain the same. We now find that because of the voltage dividers, our potential at point UA is now 0.45 volts. So an increase of the resistor R1 ends up with an output voltage of UA being positive, and a decrease of resistance of R1, the output voltage UA will be negative. Now the Wheatstone Bridge circuit always uses 4 resistors. These 4 resistors could be 1, 2, or 4 strain gauges. And so what that means that the amplifier making the measurement usually completes the missing resistors in the Wheatstone Bridge. So we would either have 1, 2, or 3 completion resistors. When we're using 4 active gauges, we get the largest output value. Alright, here's a more typical view of the Wheatstone Bridge. And in this case, all 4 values of the resistance can change. Our UB is our excitation voltage for our strain gauge, and our UA is the output result. In order to make a proper measurement, both sides of the bridge must have equal resistances. So R1 and R2 must be the same, R3 and R4 must be the same. To figure out the total value of the output, you measure the strain. So taking E1 minus E2, and then E3 minus E4, multiplying them by the K factor, the gauge factor, divided by 4, and then multiplying that by the excitation voltage, and you come up with the voltage at the amplifier. So there are 4 pretty much elementary circuits with strain gauges. The first 2 are quarter bridges with 1 active strain gauge. And the one in the upper left-hand corner, we have the active strain gauge in the northwest quadrant of the Wheatstone Bridge. The one on the left, or on the right, we have the active strain gauge in the southwest quadrant of the Wheatstone Bridge. The half bridge has 2 active strain gauges on the left side of the bridge. And on the full bridge, all 4 of the arms of the Wheatstone Bridge are active strain gauges. In all cases, both sides of the bridge, again, must match resistance. So here's a couple of examples. We have a bending beam, and we've got a quarter bridge strain gauge mounted to that beam. In this particular case, just the single resistor, R1, is the actual strain gauge. R2, 3, and 4 are provided by the amplifier making the measurement. In order to calculate a gauge factor of 2 is taken into effect, and this is written again on the strain gauge package. And if we estimate a level of 1,000 micrometers per meter, or 1,000 microstrain, we end up with an output here of 0.5 millivolts per volt of excitation. Here in this case, we have measurements on a bending beam. It's a half bridge. And so now we have a strain gauge on the top of the beam and a strain gauge at the bottom of the beam. This provides a bending load. Using the measurement equipment for the half bridge, and we have a gauge factor of 2 again, and again the same 1,000 microstrain force. Our output measurement is going to be 1 millivolt per volt of excitation. So this ends up being 2 times the output value of the quarter bridge. And measurements on a bending beam with a full bridge. And in this case we have 2 strain gauges on the top of the beam, 2 strain gauges on the bottom of the beam, in the configuration that you can see in the diagram on the right. And when we use the same factor of gauge factor of 2 and 1,000 microstrain deflection, we find out that 2 millivolts per volt of excitation is our output, or 4 times the value of the quarter bridge. Now, manufacturers of strain gauge provide a variety of orientations for differing applications. So in the strain gauge on the left-hand side of this picture, we use one for the bending beam. There's 2 strain gauges here that are already pre-mounted and oriented towards each other. And so when applying the strain gauge, you only have to be concerned about the orientation of one package versus 2 individual packages. On the tension or compression bar, we have these 2 types of gauges, which are oriented in a 90-degree difference. If we were going to make a measurement on a shaft under torsion, we can again use a full bridge configuration. And you can see that we're concerned about the full bridge capabilities. And again, we have 4 times the output of a quarter bridge amplifier. And the right strain gauge for this particular application is a chevron-based design. Another opportunity is the strain gauge rosette for stress analysis. And we have 2 basic shapes, 0, 45, and 90-degree rosettes, or 0, 60-degree, and 120-degree rosettes. And this allows you to have strain measurements in 3 directions, A, B, and C. Now, going on, we want to reduce and eliminate measurement errors, especially the effects of temperature. As the temperature errors can be corrected mathematically, and temperature can be compensated using the Wheatstone Bridge circuit by using a quarter bridge with a compensating strain gauge or half and full bridges. Every strain gauge will give out a value when the temperature varies without any mechanical load. The reason behind this is that the workpiece that you're working on is going to expand or contract with temperature. There will also be a change in the specific resistance of the strain gauge. The strain gauge grid also expands with temperature changes. So if we look at this case here, we have a temperature compensated setup using the Wheatstone Bridge circuit. So we have our strain gauge mounted on our bending beam with a downward force, and the temperature is varying. The output below is our strain gauge number 2 in the circuit, and that's also mounted to the same material, but it's not being affected by the bending event. So the quarter bridge with a compensating strain gauge, the compensating strain gauge must be applied in a spot where it will be subjected to the same interference effect as the active strain gauge. It must have the same physical properties as the active strain gauge, so it's recommended that it comes from the same batch of gauges. It must only be subjected to the interference effect and never to the quantity to be measured or its side effects. And it must be applied at the same material, example steel, as the active strain gauge. Okay, so temperature compensation using the Wheatstone Bridge circuit, there's some advantages to that. So it's not necessary to measure the temperature during a strain measurement. And it's not absolutely necessary that strain gauges are adjusted to the material. So you can order strain gauges that are already temperature compensated for certain types of material. So if you're going to be working on aluminum, you would order a strain gauge that's already compensated internally for aluminum. Or if you're going to be working with steel, you can order for that, quartz, plastic materials, etc. A typical values of strain gauge are 120 ohms, 350 ohms, 700 ohms, and up to 1,000 ohms. Typically, 120 ohm has been preferred for stress analysis. 350 ohms is preferred for transducer manufacturing. 700 ohms is preferred in a combination with telemetry systems and for measurement on materials with low thermal conductivity. Also, you'll find the values of resistances used in the United States and Europe tend to change. In most cases in the U.S., you'll see 350 ohm strain gauges. There's pluses and minuses to both. The 120 ohm strain gauge will provide more self-heating because there's a higher current flow. But there's less influence by the changing of the isolation resistance, and there's less influence from electromagnetic interference. 350 ohm strain gauges act as better antennas for electromagnetic interferences, and there's greater influence by the changing of the isolation resistance, but there's less influence from the electrical resistance in the connection paths, such as the cables, terminals, slip rings, etc. The proper transfer of the strain from the test article to the gauge requires proper adhesion of the strain gauge to the test article. So in order to prepare for installing our strain gauges, we need to plan out the application. So our first line of thought is, what is the object of our measurement? And how are we going to perform our test? Where are we going to be doing this? And then when are we going to be doing it? So what we want to measure strain. And once we've figured that we want to measure strain, we go through and say, what is the quantity do we want to measure? Material stresses, forces, loads, etc. How are we going to do this? Strain gauge. So we need to consider our conditions. It will be a static event. It will be a dynamic event. It will be a short duration test or a long duration test. What's the frequency of the tests that we're going to be running? Where are we going to be doing this? Are we going to be doing this in a laboratory in a clean environment? Are we going to do it out in the field? Are we going to do it out in a production site? Or are we going to do it out at a windmill location? Are conditions stationary or are they going to be mobile? And then when do we going to do this? Do we have time to make the preparation and acquire material, prepare the site for the installation? All of these have to be taken into account before applying the strain gauges to the test article. So when planning the installation, you want to have well-trained personnel. You need to have some sort of signal conditioning, an amplifier that will take the signal and record the data. So this could have carrier frequency excitation, or we can have DC excitation. We have to pick the strain gauge. It's got to be suitable for the type of application that we're going to be measuring. As you saw previously in the slides, we had a variety of different types of strain gauge based on the application that's required. You have to have an installation plan. What kind of strain gauge type are we going to have? What's the positioning of it? How are we going to add, put down the adhesive so that it sticks to the test article? After that's in place, we need to have a wiring scheme. We have to get the signal output back to our amplifier to make the measurement. So we have to consider the wiring, cables, material to fix the wires, etc. And then lastly, we need to consider protection for the strain gauge. We need protective coating, electrical shielding, etc. So bonding agents, what's the purpose? The purpose of the bonding agent is to transmit as much as possible without loss the deformations of the measured object to the strain gauge. We want to connect the strain gauge firmly to the surface of the specimen in order to transfer the deformation of the specimen correctly to the strain gauge. We need to provide a stable behavior over a wide temperature range. We need to prevent the strain gauge and measured object from being chemically attacked from rust, corrosion, etc. We need conditions and influences may help determine the type of bonding agent required for the specific installation. There's the possibility that we're going to be connecting various materials, even dissimilar ones. And then installation of the gauges may be required at varying temperature and humidity environments. We need to consider, will there be a reaction to the material connected, i.e. plastic. And then we've got to see whether or not we have control of the working speed. So can we use hot adhesive where the gauge is baked into place, such as a load cell or other sensors where we use strain gauges? Or can we use a cold cured adhesive such as our Z70 or other quick dry cements? Surface preparation of the metal workpiece, in this case, we need to go in and remove grease and dirt on the area where the strain gauge is going to be applied. So we need a complete mechanical removal of rust, oxides, etc. We need to level the surface that we have, either by sanding it or filing the area. Then again, we need to clean the area using an isopropanol or acetone type cleaner. We need to roughen the surface so we have proper adhesion of the gauge to the material. We need to mark the position of the strain gauge. Again, finally, clean the area one more time to make sure that it's very clean, and then prepare our strain gauge for installation. So this is an example of a large support beam, and we're putting strain gauges on at the site. A tent was built up around the area, and you can see our technician is wearing a lab coat and gloves to clean this particular area so that we make a proper measurement at all times. Next, when we prepare our strain gauge and solder tabs, you can take a piece of tape on one side of the prepared strain gauge and then lift the strain gauge off and apply it to the test article so that it's up at a hinge. So we're going to turn the strain gauge up using the solder tabs as a hinge type of setup. Apply the adhesive, usually 1 drop is sufficient, and then put down the gauge. We cover this with a Teflon foil and apply pressure for at least 1 minute in room temperature type environments. After the gauge is cured, a visual inspection is required. We do visual testing for inclusion of air particles below the strain gauge, see if there's any bubbling under the strain gauge. Make sure that we have sufficient adhesion at the edge of the gauges. The entire gauge should be attached to the material. Checking for porous soldering technique and residual flux. In this picture here, you can see you have a case where there's too much solder in the area and the solder joints are very cold. So we'll not get a good measurement from this strain gauge installation. After this, we're going to do some insulation testing, and we want to check for the resistance between the strain gauge connections. So this should be 120 ohms or 350 ohms, whatever value of strain gauge selected. Now the resistance between the gauge and the workpiece should approach infinity, greater than 20 meg or higher. Protecting the strain gauge, after it's installed and properly wired, must be protected from chemical and mechanical influences. This protection method should be decided on based on the expected life of the strain gauge. You need to consider what the environment's going to be, what is the operating life will be, and then what measurement precision is required for the test. So here's another case where we've got an installation, and this is the same type of beam that we were showing in the previous article. And we have a variety of different protective agents that are put down over the gauges. This particular pipe that he's testing here is going to be placed in the North Sea and faces all sorts of nasty environments, including salt air. After everything is wired up and protected, we need to consider our wiring. So we need a suitable solder point has to be determined. Shielded cables to prevent or reduce error from electrical and magnetic interference should be used. With quarter bridge configurations, a simple 2-wire connection should be avoided because of cable resistance changes due to temperature changes. We can also use sense lines to correct for possible loss. HBM has a series of webinars that are available that have already been performed, and there's one on improving your wiring connections that I would recommend that you review if you've not seen that already. Once the strain gauge is fully wired, we need to consider using high gain amplifiers. Since the measurement values are very, very small, the signal must be amplified before it can be recorded. And because we have the high gain amplifiers, we also need to make certain that our amplifiers are low noise. We need to eliminate additional noise from outside sources, and this requires an amplifier that is very low noise. So here's an example. We have a good soldering technique. We have a gear wheel here, and we have a variety of different strain gauges mounted on the gear wheel. And the wiring is placed such that it's protected from the live test and is able to make measurements over dozens of channels. So in conclusion, The strain gauge is a very useful tool for making structural measurements. Proper installation of the strain gauge is key to making these valid measurements. The strain gauge is a small, inexpensive, and accurate tool for making your measurements. So, thank you very much. If you have any questions, you can go ahead and type that into the WebEx chat dialog. Several technical documents are available on the HBM website, such as our introduction to measurement using strain gauges that are available in PDF download format.